Remnant or remnant? Arigatou gozaimasu, Niebi-san. この番組はフランススポンサーを提供いたします。Oh, I fucked that up. I'm not here yet because, as I just said, the following program is presented thanks to our sponsors who you will be hearing from soon. Not our sponsors, it's just ads. 3 minutes of ads and then the stream starts. Yike. Just the jargon file. The regular ass jargon file. Were they called AI cones all this time? I'm having AI hype induced Mandela effect. Hello. It is me. Actually. We were engaging in a little bit of bait and switch as a treat. Oh, hold on. This says the ads are in progress, but the other thing said the ads are over. And it's not 3 anyway, but when the ads are over, I'll be here. And until then, I'll also be here. Okay, but now it's 3, so now we should definitely start. Hello everyone, welcome to the stream. It is me, Ember. Starting a little bit later today. You know, this happens sometimes. We were running errands and stuff. Things took a little bit longer than we would have expected to, but we're excited to be here and to get to put on a stream for you all and to do a little bit more code practice and to take the stream starting soon off the screen, because the stream has indeed started now. Not soon, now. So, without any further ado, let's just dive in. Oh, did I make a wolf howl of that one? Oh my god. Medi, if it's up to you, people would never get to see us on stream because we'd just be so small. Favor, you'll have to help me because you're still big and tall. Today we're focused on solving complex algorithm problems using Python dictionaries. The data structure that enables us to store data in key value pairs. Is this just going to teach me how to use dictionaries? I think I already know how to use them. This powerful data structure facilitates lightning fast retrieval and insertion operations. Well, that's why you call it practice, right? It's because you got to keep getting better and better at it. It gets easier. You have to do it every day. That's the hard part. We'll be tackling 2 carefully selected problems designed to highlight the practical uses of dictionaries: the majority vote problem and implementing a keyword index. These problems serve to illustrate real-world applications of dictionaries, helping us understand them in a deeper, more meaningful way. Let's dive in. Our first problem is about identifying the majority elements in a list. The majority element in a list is an element that appears more than n over 2 times, using the half plus 1 rule, right? Given a list of integers, our aim is to identify... Oh my god, it's a Kane like remix. I'm not sure that I support people doing this with this song. It's not bad. We need to play it near on stream. It's definitely on the to play list. The problem could arise on numerous occasions. Imagine running a survey where a participant selects a number from 1 to n to rate a product. You want to find out if there is a feature that reserves more than n over 2 votes. Are you... Is this n supposed to be the same n? Because I thought this n was out of all what? One naive approach is for each element, iterate over the entire list and count the number of occurrences. However, this approach could lead to O to the n squared time complexity, which is not suitable for a large data set where n is the size of the list. A more efficient approach is to use a Python dictionary to count the occurrences of each element in the list. If the count of any elements exceeds n over 2 at any point during our iteration, we immediately return that element as the majority element. If no such element is found, we return -1 after we've iterated through all elements. Okay, so that makes sense. That's like calling off an election once you know a candidate has the required votes that cannot be beaten. Let's break down the solution step by step. First, let's set up an empty dictionary, count dic. Oh, count dic. Man, the count. This dictionary will help us keep track of the count of occurrences of each element in our list. We iterate through the elements of list A. For each element, we increment its count in count dic. If the count exceeds n plus 2, okay, fine. Blah equals count dic dot get element, 0 plus 1. I'll use get to assign 0 if it hasn't been. Oh, this is good to remember. I need this. I needed this the other day when I was working on something and I couldn't remember it. It's the value of itself, and if it has no value yet, it's just 0, and then plus 1, and then you assign it. And so now, perfect. Bar 2. Such a default value is a common approach in problems where the answer may not exist. The final solution looks like this. Back in the day of like C++, it was pretty standard to have like -1 be your error. And I guess you could use like multiple negative returns for multiple errors, but obviously only in cases where you expected the answer to not be a negative integer anyways, then you couldn't do it. But it is interesting because it works with any type of list, not just ints. But then, so like this could be anything because there's no type hinting, right? This function could return string, or it could return int, and that is madness. Do you think we can apply default dic here? How will the code change? Oh. We could default it to be a default dict of int with default value 0. And then we don't have to do this. We can just do plus equals 1. Implementing a keyword index. Moving on from counting pair frequencies, we'd arrive at our second problem, creating a keyword index. And in this situation, we're giving a list of strings, with each string representing a document. Our task is to generate an index of all the distinct words in the document for quick reference. We need to create a dictionary where each unique word is a key. And the corresponding value is a list of indices pointing to the documents where the word can be found. Problem actualization. Actualization. Actualizing. Actualización. Imagine you're building a search feature for an app, and you need a function that quickly retrieves all documents where a certain keyword is present. If you have ever searched for something using your browser's Control F or Command F function, you have utilized such an index. Our task is to create a dictionary that behaves like such an index, mapping a keyword to all the documents where it can be found. A naive solution to this problem could involve iterating to the entire list for each word, storing document indices for each word. While this approach does yield the outcome we're looking for, it is inefficient with a time complexity of big O n squared. But dictionaries provide an efficient solution. As we pass through each document, we update our dictionary. Each word becomes a key, and every time we encounter it, we append the current document's index to the list of values for that key. This approach requires only linear time in the total number of words in all documents. A significant improvement on the previous method, so it's just n. Let's work through the solution. We first initialize an empty dictionary index, then we start looping through our list of documents using an enumerate. For each document, we split each document into words, and for each word, we check if it's already in our dictionary index. If it is in the dictionary, we append the current document's index to the list of indices for that word. If the word is not in the dictionary, then it's the first time we've seen this word, and we add it to the index with a list that contains the current document's index as the value. Here's how to do it. Keyword index docs. Index equals brackets. For doc index, comma doc and enumerate docs. For word in doc.split, if word in index, you're always checking, you're always looking for it, and then you will append the doc, because it's just however like a doc is, but it's just the index, it's just a number. In your list of documents. Hi Nosy, welcome to the stream. Otherwise, you make it a list that only contains the index. So for the first time you encounter any word, it'll just be there. But if it's just a list and you're appending each time you've already seen the word, if the word appears multiple times in a document, you'll append the document multiple times. And sure, that tells you that it's multiple times in the document. It's gonna look messy. In this lesson, we have taken a hands-on approach to solving practical problems using dictionaries in Python. Throughout these problems, we have learned how dictionaries can be used to efficiently track frequencies and generate indexes. Indexes? Indices. I guess they can both be correct. Two tasks that are widely used in real-world applications. To recap, we have covered understanding the problem statements and their real-world relevance, analyzing both a naive and an efficient approach for solving the problems, implementing and understanding the optimal solution using Python dictionaries, observing the power of dictionaries in action, demonstrating how they improve efficiency by reducing computational time. Now that we have covered the theory, this is just copy. It just says the same every time I read it. If you need to hear me read through that, just go back to the first time I read through it. It's not a simple majority of this one. Again, all of these problems have like weird like employment applications. I wonder if it's on purpose. Imagine you're in a corporate setting and you have a list of employee votes represented as integers. Oh wait, I can have him read it.
All right, my friend. Time to put on your coding cap.
Oh,
Imagine you are in a corporate setting and
need
you
a
have a list
hat.
of employee votes represented as integers like A1, A2, N dollars. These integers actually represent the IDs of your fellow employees. And yes, people can indeed vote for themselves. An employee gets elevated to the exclusive board member position once they
Exclusive
earn
board
at least
member.
N3 votes, with N being the total number of votes. Your task, find out the ID of this popular employee. If no one hits the vote mark, return navs1. If multiple employees received at least N3 votes, return any of them. The votes are delivered to you in list format. As an illustration, 1, 2, 3, 3, 3 means employees 1 and 2 voted for themselves, and employee 3 received 3 votes. Hang tight, there can be edge cases, such as no votes or everybody voting for themselves. Your end goal is to return the lucky candidate's ID if they secure a seat on the board. If no one qualifies, return -1. Got it, superstar? Now it's time to put your coding practice to the test
Superstar.
and sort out this corporate election pronto.
Oh, I'm a superstar. Um. Oh, thank you, Nieves. Employees 1 and 2 voted for themselves. Okay. No votes, or everybody voting for themselves. If no one qualifies, so it's just like, alright. Four-member in vote. Import collection. I'm gonna do the from collections import default. And we're gonna say vote totals equals default big in. Hi Jams. Remember in vote. Vote in vote. Vote totals dot vote plus equal 1. If vote totals vote greater than or equal to len vote over 3, return -1. So what this does is it goes through your list of votes and it's like, okay, 1, so there's 1 1, okay, there's 1 2, okay, there's 1 3, okay, there's 2 3s. And every time it checks. Are there more than 1, 2, 3, 4, 5? Are there more than 5 over 3 trees? And eventually it'll be like, yes, there is. Um, but I don't want it to return. There can be such as anyone who gets n over 3 votes. It says return any of them. Okay. So you can also get lucky because it's not return all of them. I just need to return one, which this should do, and it's like, well, you know. Uh, hmm. For voting votes, vote totals of vote totals must be this. Do I use the full dict? Plus equals 1. How could it be 1? If it's greater than... Wait, why greater than or equal? 5 over 3. 5 over 3 is about 1. Well, that was it. That was the problem, but is this correct? By using this, I... What does this even print? It's 1. So that for this one, anyone who received more than 1 vote would count. What's the double slash mean in Python? For floor division. I don't know if I want to do floor division. Maybe I just want to do normal division. But that should see us. Like, it should see us through with no problem. But, you know, never works. Beautiful.
Hey there. I've got a stellar task for you where you gotta be like a cosmic librarian. You know, we got gazillion documents in the universe, each represented as a string in a list. Your task is to whip up an index that's as nifty as a dictionary, which logs in every unique word from these documents. Now don't forget, each unique word is a key, mapping to another dictionary where the key is the document index, and the value is how many times that word appeared in the document. It's sure going to make searching a lot quicker, kind of like quantum speed. Eh? Let's get rolling.
Kind of like
Make
quantum
sure that your code
speed,
handles all
hey?
the edge cases. The input would be a list, where each string inside the list is a document. And every string is just a regular English text. Easy peasy. The output should be a dictionary, where each unique word is a key, and the mapped value should be another dictionary, having document index as the key and its corresponding word count as the value. All right, time to hit the hyperspeed.
Okay, so it's just, again, you do for dog index, dog in enumerate dogs. Let loose the dogs of war. And then it's a dictionary of dictionary. And we can do this, we can also do this with the default dict. So we would do from collections import. Then you're like, okay, need to make the index dict, which equals a default dict, which utilizes a lambda function that lets you know that do this. I think I just need to make a dictionary inside a dictionary. So we can just call this, just make this dict, formalized dict with no default value, and then we can do for word in dog.split. So now you're gonna start a little dog dictionary, but it's a index dict sub word sub dog index plus equals 1, right? And this is not gonna work because it's gonna give me a hey. And we could do it with a get, but I wonder if I can do it with a lambda. You'd say the default dict lambda and maybe x. You say the dictionary of the form can't do it. I don't know how to do it. I'll maybe check. I'll maybe figure it out after. But let me see. The other way to do it is to say if word in very simple dictionary. If word is an index dict stop, it's here. You can say word. You can say index dict of word doc index plus equals 1. That will take for the index and it will add like a count. And if it is not already an index dict, what I need to do is I need to create a dictionary. Well, if it's not, then you do index dict sub word equals dictionary with dog index as the key and 1 as the count. The word is not an index dict, so we can just set the count, but we just saw it. So just set it to 1 and move on. And then return the index dict. Okay, enumerate is spelled with just one N. And keyword in. File expected output. Print keyword index dot. Do you not like that? I don't see what the problem is. Key error 1. Oh, you try to access a key that doesn't exist. But we said you should create a sub-dictionary. If the word's not already an index dict, oh, but just because the word's already an index dict doesn't mean that there's already an entry for doc index, but we can do the other trick, which is to say which equals we say get the dog's index, the default 0, add 1. Hello, world. Okay. Needs a little bit of work. Probably because of this. Because this runs regardless. You can do. This should also take care of it. So if word is not already an index dict, we say, okay, initialize that as a dictionary that has the word with like a thing. And then for every subsequent instance of it, you're gonna say the index dict. So okay, here we go. Here's the problem. Still do need the second index here, otherwise it's gonna get rewritten. 0 1 1 1 of 1 1 Python 1 2. Is there a way I could have done this prettier? Do I care? This looks nice, but it's so messy. Does it look nice? How can it look nice and messy? It doesn't look nice, it's just nice that it's one line, right? But I feel like I'm chaining all these little tricks, and it would be way more readable, and it'd be way easier to remember later what we were doing if it was not like that. Code readability, people. It's all about. But you know what else it's all about? Moving on, because I don't care that hard. Practice. Fireworks. Alright, look, we get to start a new lesson, this time with sorting and searching algorithms. So I wonder. So, well, let's see. Let's see how good this is. We have about 20 more minutes in the stream before we want to wrap up. So that might not be enough to get super deep into the lesson, but we can start reading it. Welcome to our hands-on lesson in which we explore the fascinating concept of recursion on practice. Recursion on practice. Throughout this lesson, we'll peel back the layers of three foundational problems: generating the Fibonacci sequence, finding the sum of all elements in an array, and calculating factorial. A factorial is when a number is really excited. It's like 5 and it's 120. 5 is 120. Don't believe me? Look what happens if I Google 5. Okay, 5 is 120. 5 is of course just 5. 5, right? 5 is just 5. But 5 is 120. I feel so bad because I was making a joke, a pun, but Baby was so excited about 5. They just was too committed to making my joke about factorials. Look at her. She's covering her face in shame. It's okay, Faybot. Uh, I can't pet you, but maybe I can like. There you go. Good road. E. E. I need to make a Faybot I can talk to out loud. Oh my stars! The Fibonacci sequence. That's so magical and mysterious. No, Faybot. But maybe Cosmo the Space Dog can. Right. We'll systematically deconstruct each of these problems, expose the core of each solution, and then rebuild them. If the name Fibonacci reminds you of Fibonacci the Piso, one of the most famous mathematicians of the Middle Ages, renowned for his work on the Fibonacci sequence, you're not mistaken. I feel like most people know about the Fibonacci sequence, don't know about Fibonacci the Piso. Wasn't he from Pisa? Wasn't he from the... Oh, is this wrong? Or is Pisa called Piso somewhere else? Bernardo of Pisa. This website, dude. Like, no one reads anything anymore. No one cares. Where's Fibonacci from? Ah, wherever. He's from the floor. Fibonacci of the floor. One of the greatest mathematical minds of his generation. It's alright. It does sound cooler than Leonardo. Can't argue with that. Can't argue with that. Fibonacci. I wonder if that means something. So what is the Fibonacci sequence? The Fibonacci sequence is an infinite sequence of numbers starting with 0 and 1, with every subsequent number being the sum of the previous two numbers. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 50, 55, 89. Given a number n, our task is to implement a recursive algorithm that returns the nth number of the Fibonacci sequence. Remember, indexing starts from 0, just like Python's zero index style. Flame wars. Visualizing Fibonacci might be a little bit tricky at first. If you're into art and design, you might have heard about the golden spiral, a logarithmic spiral whose growth factor is linked to the golden ratio. Interestingly, the Fibonacci sequence is connected with the golden ratio as well. If you look at the ratio of two consecutive numbers in the Fibonacci series, you'll observe that it approximates the golden ratio. It is truly fascinating to see such a foundational mathematical pattern connected to art and design. It's like baby's first golden ratio. Speaking of golden ratios, welcome Golden Glory. We have a lot of gold in the stream today. Very gold stream. The naive recursion approach. And glory. Yeah, plenty of glory. Here we present a straightforward recursive method that returns the nth Fibonacci number. And then it's just, if n is greater than 1, return n. And if n is less than 1, return n, because 0, oh, that's funny. 0 is 0 and 1 is 1. And this once and for all answers the question of whether 0 indexing or 1 indexing is better, because 0 index lists have the benefit of the first two elements of the Fibonacci sequence matching the indexes. Otherwise, return Fibonacci of n-1 plus Fibonacci of n-2, which will always like have to add every single like number up until like it'll just go through the entire Fibonacci sequence, generating all the other numbers by virtue of adding two of them together, because it'll just make, basically this can only return 0 and 1, right? So it'll just make like a huge sum of pluses of ones up until the value that you're looking for. Which we might prefer to do it differently. The inefficiency can be seen by looking at how many times the program calculates fib of n-2. This function is called once in the scope of fibs of n, a fib like telling a lie, and then gets called again in the scope of fibs of n-1. This redundancy in calculations greatly bloats up the time required to execute the program, leading to this solution's inefficiency. For instance, when calculating the fifth Fibonacci number, the third Fibonacci number will be calculated twice, and the second Fibonacci number will be calculated 3 times. You can even see that in general, the n Fibonacci numbers will have to calculate the n-2 Fibonacci numbers n-1 times, which is incredibly wasteful and inefficient. In fact, this approach has an exponential time complexity of O2 to the n, which means the runtime doubles with each addition to the input size. That is terrible. It's funny, n to the second power is way better than 2 to the nth power. For mathematical reasons. Ideally, we would want to reduce this to O of n, which signifies linear time complexity, a much more efficient rate. This can be achieved. Bold claim. By handling basic cases in the naive solution, we integrate an optimization technique known as memoization to further enhance the function. With memoization, we store the results of previous Fibonacci number calculations. This way, for any given input n, if we already calculated the Fibonacci number for n, there's no need to recalculate. The function can directly return the stored results. So you can do it with hash maps. The combination of addressing base cases and leveraging memoization avoids unnecessary repetitions and improves the function's efficiency, particularly for large inputs. Let's look at how memoization can improve our solution. Death bit and computed. And it is indeed, you just pass a dictionary where that keeps growing each time. If n not in computed sub n equals fib n-1, and you pass however much you've computed so far, And by the time, and eventually n will like already be incomputed, and you can return. Oh, that's funny. Yeah, you return the value of n. You can compute it of n. In this function, we use a Python dictionary computed to store the Fibonacci numbers we've computed so far. It's funny how you can then you put your base cases directly in the arguments as like the default argument of the function. I like that. It's kind of cute. If a number n is not in a dictionary, we calculate it using the recursive formula and store the result in our dictionary. Then, as you're doing this, you're creating all of these new versions of this dictionary that go off and do go God knows what, and then they fill up, and then like they don't get to share it ever, even though like this 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 will likely create further instances of the function, and this will also create further instances of the function. We don't know if at any point this will be calculating a number that will already be in this computed in the set that this like branch has done, because it basically starts branching out. Except of course if one of them is already computed and then gets returned, and that starts to collapse the branch. And be cool to like it'd be cool to like do some sort of animation that shows the execution tree for various Fibonacci numbers. This at start in 5 minutes, so we're gonna snooze, give us an extra 5 minutes, and then in 5 minutes we'll start wrapping up because it's been an hour and a good amount of practice. So in this function, we use a Python dictionary computed to store the Fibonacci numbers we've computed so far. I already read this. Edge cases, results, n equals 0 are stored in the computed list by default. This function now computes the n Fibonacci number in linear time, which is a significant improvement over the naive recursive implementation. Each number is calculated only once, and the function can handle a large n efficiently. Well, maybe. Problem 2. Summing array of elements. Next on our list is a simple operation we frequently perform in our daily lives, which is finding the sum of numbers. Like, yeah, I don't doubt it, but it's so funny to think about it. You're like, oh man, it's time to find the sum of these numbers. Our task is to implement a recursive algorithm that calculates the sum of all elements in an array. You must be thinking, well, adding numbers is easy. I do it all the time when I'm grocery shopping or counting the days left until the next holiday, right? Adding numbers is easy. I do it all the time. Absolutely. We regularly sum up numbers. But what about numbers in an array? Well, I never do that. It's not true. The other day I was doing sums because I was exercising, and we were doing like a decreasing number of reps each set. So it was like 20, 18, 16, 14, all the way up to 2. And, and I was trying to figure out like, okay, how many reps total that is. So I was literally summing through an array. So it does happen. It does happen every once in a while. Mind you, I was doing this in my head at the same time as I was doing the exercise, so I had a bit of an added like difficulty component for for my concentration for both tasks. I think it's 300, right? Yeah. We'll find out. We're always sum of numbers. But what about numbers in an array? Imagine trying to add up pages of a manuscript. Instead of summing each page as you go, which can be repetitive and prone to error. See, if only, like, if I had the, because I know, like, okay, there's a formula, right? I guess there isn't a formula for an arbitrary array. There's a formula only if the series has like a specific pattern to it. You sum of the first page with the total pages of the remaining manuscript. Sounds much more natural, doesn't it? For loop approach. Sure, directly adding up elements using a loop is straightforward. However, just like in the case of the Fibonacci sequence, it misses the significance of understanding and appreciating recursion. So let's adhere to our recursive path. Recursive approach explanation. In a recursive approach, we decompose our problem similarly. We consider the sum of the array as the sum of the first element and the sum of the remaining elements. It's almost as if we're peeling the array one by one and summing it up layer by layer. I get it. So you just say it's the first element plus, and then you call the function again on all the other elements. But how does that make it exactly better? Guess we'll find out. Instead of considering the base case as an array with a single element, we modify our approach to use an auxiliary index. We initially set it to 0, pointing at the first element in the array. The base case is now when index equals the length of the array. Ugh. Big cat yawn. At this point, we have processed all elements in the array, and the function is to return 0 as there are no more elements to add. For arrays with more than one element, the function effortlessly adds the current element, pointed at by the index. So yeah, so by including this index, we get to do the memoization. And the sum of the remaining elements. It achieved this sum by recursively calling the array sum function, now passing index plus 1 as the index. This incremented index moves the pointer to the next element. This way we can visualize it as moving along the array, adding one element at a time until we reach the end. And this is better because this just adds what we had so far. This index-based approach eliminates the need for slicing the array, making it more space efficient. With these modifications, our final solution is if the index equals the length of the array, that means it starts at 0. If it's 0 or if it's the last one, yeah. By the time we get to the last element, you can turn 0. What? I guess because the first time you call it, you never call it with an index. So we take the first element plus, and then we do the sum of the array starting at the second element. And then add that element, we will add okay, so this, I understand why this doesn't add like memory complexity because it just uses the same array. It's just always checking in the array, but not really that efficient. Either ways, so no stream tomorrow because it's that job interview we've been talking about. I think, I think we will. That's funny. Just let me know that there's a tool for finding rates. I think we will stream on Friday. But and then we'll just do our video game stream on Friday, but we'll see. So no stream tomorrow. Wish us luck. And yeah, have a great day. I was like, I want to rate someone. I want to rate someone. It's too much effort. All right. Ciao. Take care. Bye.